This time we are going to do something, we're going to work with something called the transportation and network models. Now, a common problem in supply chain management or logistics is how to get something from the factories to where it needs to go. So from a source of supply to the customers. How do we allocate the amount of transportation? How do we say that one factory should produce a certain amount and another factory should produce another amount? And how much of that goes to which customer? Now, this problem, we've got Kiwi General Company, their supply chain manager Don he's got 2 factories and he's got 4 distribution centres or DCs for the customers. So each of the chains of stores that sell the jandals from the Kiwi General Company have a distribution centre. So that's like a central stock of inventory which is used to supply their stores. So as far as Kiwi Jandals is concerned, they have 2 factories, one in the North Island and one in the South Island. And there's 4 distribution centres throughout New Zealand that they have to supply. Now, on page 2 of the PDF document, which gives us the instructions, we can see that there's 2 factories with different supply and 4 DCs with different supply. And Don's also provided us with a table 3, which provides shipping costs. So these are the shipping costs per unit from factory 1, from each factory to each DC. So what we have to do is figure out the best method of getting the jandals from the factories to the distribution centres while making sure that we meet all the constraints. So we can't produce, if we look at table 1, we cannot produce 100 pairs of jandals in factory 1, even though it might be the cheapest from terms of transportation. So we've got some constraints there. We've got the constraints from the factories, which can only supply a certain amount, and we have some constraints in the distribution centres which only demand a certain amount. So we cannot send out more from a factory than we can supply from the factory, and we cannot send more jandals to a distribution centre than they have demanded. Now, what we're going to be doing in this lab is, it's a very short one, so we are going to be working with a blank template. So by now you should have a very good idea of how to do this. So first of all, I'm just going to set up a table like table 3 there of shipping costs. So four distribution centres, and 2 factories, and I just put the values in from the table on your instructions. 14, 9, 16 and 5. And what we can do is we can change the format there to dollars just to make it clear about what we're doing. We don't need any decimal places because it's whole dollars per unit. And now we need another table that deals with the actual shipments. And this is going to be exactly the same sort of table. 4 distribution centres along the top. In fact, since it's almost the same, I'm just going to cut and paste. Oops. Now, what we want to do here is we want to make sure that we have the capacity constraints from the factories, and we also have the demand constraints that have been met. So we need to send the customers as much as they've demanded, not less, and we cannot oversupply. So now I can make all this very pretty by adding bits on the table. So what I'm just going to do quickly is I want to add some extra parts here. I want to say these are the number shipped, capacity, and I'll just add some borders here just to try and make this whole presentation look a bit tidier and easier to follow. Okay. Now, what we've got here is, if we look at this column, we have got the shipments going to distribution centre 1. Down at the bottom we have the number received, which is going to sum the shipments from factory 1 and factory 2 to distribution centre 1, and we're going to have a constraint to make sure it's greater than the demand. So some of this we can fill in already. We can fill in the demand from table 2, and the number received has to be greater than or equal to demand, because we don't want to disappoint our customers. Now in row 12 here you can see factory 1 was shipping a certain number to distribution centre 1, to distribution centre 2, to DC3, to DC4, and then there will be a total number shipped there. Now the total number shipped has to be less than or equal to their capacity, and we can fill in the capacity here, looking at the instructions. That is the amount of capacity that we have. So we're beginning to build up the spreadsheet here. Now the number shipped will be equal to that, will be equal to the total shipped from factory 1 to factory 2. And we sum the number received in each factory. So we've entered the demand constraints and the supply constraints, and we'll just add some figures in there to make sure it's working okay. And those numbers seem to be adding, so the spreadsheet seems to be working well. Now we're going to find a total cost. And we're going to be putting it in this cell. Now the total cost will be, now I just want you to see that we have two arrays here, or two matrices. Now just have a look here, we have a matrix here, and we have one here. Now note that these two matrices are very similar. They're both got DC 1 to 4 along the top like that, and they both have factory 1 and 2 down the side. Now the cost of shipping 2 units from factory 1 to DC 1 will be 2 units multiplied by $8 per unit, or $16. Does that make sense, I hope? So to ship from factory 1 to DC 2 in this example, we've got 6 units entered into this cell, so the cost will be 6 multiplied by $6 per unit. So to find out the total cost, we want to multiply that cell by that cell, add it to that cell by that cell, and do that for the entire array. Now that can be done by hand, but again we're going to be doing this with a spreadsheet, and we're going to use a function called SumProduct. Now you see here it says returns the sum of the products of corresponding ranges or arrays. So the product is given by multiplying one array by another array. So first of all it says enter array 1, so we take one array, we hit comma, and then we enter the next array and we're done. So we want one array multiplied by the other array. In this case it would currently be $334, and it's that simple. Now the key here is to run solver. So we go to data and solver. Now we should be quite used to running solver by now. So the target cell will be there. Now we want to minimize our total costs like normal, I think. Now what do you think we want solver to change? Well, our costs are fixed. So these costs of shipping a unit from a factory to the distribution centre are fixed. That's given to us by our shipping company, by our courier company, so we cannot change that. What we want solver to change are these cells here, the actual amount sent from one factory to one DC. So we've got some numbers on there, but as you can see here, these numbers that I've added in as a test, they don't meet these constraints, even if they're meeting these constraints. So we want solver to give us, as usual, the optimal answer. So loading up solver again, setting our target cell will be the total costs. We want to minimize it. We want it to change these cells here, so the amount that we're sending from a factory to a DC. What constraints do you think we're going to have? Well, a shipping company isn't going to let us ship half a unit, so we're going to add, first of all, we have to only ship entire boxes of jandals, so we can't ship half a box. That makes sense. And then we have our shipping constraints. So the number shipped must be less than or equal to the actual capacity of the factories there. Now the other similar constraint is the number received by each distribution centre must be greater than the number that they demand. And we're done with the constraints. So we've only got 3 constraints. We can click options, we'll assume non-negative, we don't want any funny negative numbers in here. Now what would a negative number mean? Well, if we look at this first one, from factory 1 to DC 1, if we had a negative number there, instead of sending a unit of production from the factory to the distribution centre, a negative number would imply that instead of flowing from factory to DC, we are flowing from the distribution centre to the factory. Now that doesn't make any sense, having a distribution centre sending a finished good to the factory in this case. So we don't want any non-negative numbers. This means that all of the flows will be fixed from a factory to a DC. We will assume a linear model as well, just because it's going to increase the speed at which we can solve this problem, but it will be solved very quickly. And I think also I'll change the tolerance to 0, and we're going to go for an optimal solution, and you can see that was fast. So this is a very simple problem, really. There weren't a lot of constraints, there weren't a lot of difficulties there, and this has given us an optimal solution. And what it means in this solution, or how we'd interpret this solution, is factory 1 is sending 40 units to DC1. So DC1 is actually happy. They've got 40 units in total, and they're all from Factory 1. Factory 1 is also sending 25 units to DC3. And you'll see at the end here, that means Factory 1 has dispatched 40 plus 25 units is 65 units, which is equal to the capacity. Factory 2 has sent 25 units to DC2, and that is going to meet DC2's demand. Factory 2 has sent 20 units to DC4, and that meets DC4's demand of 20 units. Factory 2 has also sent 10 units to DC3. Now that means DC3 has received 25 units from Factory 1 and 10 units from Factory 2. That means DC3 has received 35 units in total, which meets their demand. Factory 2 has dispatched 25 plus 10 plus 20 units, so that's 55 units, which meets their capacity. And Solver's told us that this is the lowest cost plan. So to dispatch these boxes of jandals to those distribution centres would cost the Kiwi Jandal Company $1,055.